Hello everyone and welcome back to the channel CSAI Think Tinker Learn. Today we are going to dissect the distributed database. We are moving beyond simple sharding and into a complex world of cross-shard queries, joins and aggregations at scale. How do you keep a system fast when your data lives on 6 different machines? Before we jump into the architecture, please like, subscribe and share this video with your engineering team. And don't forget to visit our site, bit.by-token.com, your home for deep dive system design guides across software, data, AI, and machine learning engineering. This is what it looks like, a brief navigation view for you. Different sections for software, data, machine learning, AI engineering. Within software, you can look for fundamentals where you can search for different items. For example, if you want to look for WebSockets, all of the articles are distributed based on basics, advanced, and expert combinations. Then we have example solutions on different guides. We have tried to make it as comprehensive as possible. We start with functional, non-functional requirement. We go for the scale estimation. We look into the data model. We try to cover the sequence diagrams, how call flows. We further look at various scalability and availability options, database sharding, replication, and things like that, depending on specific use case being discussed. So please navigate to the site, navigate, and I'll provide the link in the description below. Please provide your feedback on how we can make this website even better and more useful for budding engineers like you and myself. Okay, let's come back. So let's get into this blueprint now. All right. First, let's clear up a common junior mistake and the difference between the partitioning and sharding. Partitioning keeps your data under one coordinating process. It's all happening in memory on one machine. Sharding is the fleet approach. Each slice lives on an independent machine managed by middleware. And remember, sharding isn't just about replication for safety. It's about splitting different data to scale out your total capacity. Now, crossing the boundary costs everything. Inside a single database, a join is a free local operation. But as soon as you spread data across machines, the assumption completely breaks. You're now dealing with network round trips, serialization, and partial computation. If you're not careful, a knife cross shard join won't just run slowly, it will generate terabytes of traffic and cause a total system outage. This leads us to the scatter gather and fan out trap. The coordinator fires a query to all shards and waits for the merge. It looks elegant, but it creates a straggler problem. If one shard is struggling with hot data, the entire query stalls. Plus, because of the ON fan-out growth, every new shard you add makes your system slower. Naive queries don't scale, they degrade. So, how do you fix it? Strategy 1, co-partitioning. The best cross-shard join is the one you never have to do. By partitioning your users and order tables by the same key, like user underscore ID, you ensure both records live on the same exact and the same physical disk. The join becomes a purely local operation. It's highly efficient, but keep in mind, it's inflexible. You can only co-locate by one key at a time. Second, broadcast joins. If you have a small dimension table, like a list of countries, copy the entire table to every shard. Now every shard can resolve its join locally without moving a single row from its massive fact table. Just watch your memory usage. If that small table grows over 100 MB, you're turning a performance optimization into a memory bomb. Strategy 3, semi-joins and Bloom filters. Filter before you move. If we build a compact fingerprint of the smaller table using a Bloom filter and ship that to the shards. The shards can discard irrelevant rows locally before you ever hit the network. You trade a tiny 1% false positive rate for a 95% reduction in network IOs. It's a massive win. Strategy 4 is shuffle joins and the skew problem. When tables are massive and unaligned, you have to read out all rows from both tables so matching keys land on the same machine. But watch out for the hot key. If 30% of your traffic belongs to one user, that node will melt while others just sit idle. The fix? Key sorting. Append random suffixes to your hotkeys to force them across multiple partitions. Now, let's talk aggregation. Use a two-stage pattern. Never try to average an average. It's mathematically false. Instead, ship small tuples from each shard to the coordinator and calculate the final result there. Always compute partial aggregates locally first. When you have thousands of shards, a single coordinator merge becomes a bottleneck. We solve this by tree aggregation. By introducing intermediate merge nodes, we turn a linear bottleneck into a highly efficient O-log n tree. This is a structural backbone of heavyweights like Google MapReduce and Apache Spark. For massive dataset, we use approximate aggregations with hyperlog. Perfect accuracy takes minutes, but HLL takes milliseconds. It provides a count distinct over billions of items using only 12 KB of memory, with an error rate of less than 1%. You can even merge HLL sketches from different shards with zero additional error. Let's look at how production systems handle this. The Spark pillar uses adaptive query execution to detect skew at runtime and switch strategies. BigQuery relies on a petabit network fabric to make shuffling cheap, and the Cassandra pillar avoids cross-shard joins entirely by forcing you to denormalize at write time. Every giant has a different philosophy for managing this complexity. Here's your decision framework. Alignable key, go for the co-partitioning. Small table, broadcast. Highly selective, Bloom filters. Large and unaligned, shuffle joins with salting. In your interview, remember the golden rule. Minimize bytes moved across the network. The shard boundary is just the network. Carry as little luggage as possible. What's your go-to strategy for handling complex joins? Let us know in the comments below. And again, do check out the website bitbytoken.com. The link is in the description. Don't forget to like, subscribe, and hit that bell for more deep dives. See you next time. Have a wonderful day. Bye.